and let's just leave that at the default. So that's the plot we get, and so this is how, if we require, let's say, a flow rate of 5 kilograms per second for M3, then this is the value of M1 that we need to apply, and that's the value for M2. So those are the required flow rates to produce a flow rate of 5. Right, so that's a very simple example. Now let's look at doing the same thing using our vector matrix type formulation. So that's the solution we had there. So now let's pose this as a set of matrices and vectors. So let's say we create the matrix C, where C is of this form. So you can see on the top row it's xa1, xa2 minus xa3, the second row 1, 1, minus 1, and so on. And we've got here our set of mass flow rates assembled in the form of a vector. So m dot is are these individual flow rates, and we've got this vector B here as well. So let's verify first of all that this is the original set of equations. So if you were to take the dot product here, if you were to take this top row and multiply it down the column here, you have effectively m1 times xa1 plus m2 times xa2 minus m3 times xa3, right? And that is equal to 0, right? B is equal to 0 in that row there. So if you dot multiply C and M, then you get in the resulting vector, the first value will be xa1 times m1 plus xa2 times m2 minus xa3 times m3 being equal to 0. And you can see in our first part of the solution that that's the same as this equation, right? If we take this term and write it on that side, then that's the same as the equation we get from the top row here. Right, let's take the second row. If again you take the row here and multiply down the column, then you've got m.1 plus m.2 minus m.3 is equal to, and the second position here is a 0, so that's equal to 0. In other words, it's the same as this equation if we take the m.3 on that side and set that equal to 0. So that's the second row. And the third row here, we can see 0, 0. In other words, it knocks out these two elements, leaving us with m.3 being equal to, and the last element of B there is a k. So m.3 equals k. That's what the last line gives us. And that's where we simply specify the different values for m.3 as we pass through this line here. So this is indeed the system of equations that corresponds to that physical problem, and we can use this now to solve for the unknown set of mass flow rates m dot. If we look here, we can do that simply by inverting matrix C and multiplying by both sides. Then we get here m dot is equal to C inverse times B, and so let's write the code for that. So let's just clear the screen here, and then let's develop matrix C first. So if we look at matrix C, let's look here. Matrix C is that set there, so let's just write that through. So that's xa1, xa2 minus xa3, and then the next line is going to be 1, 1, minus 1, and then for the last row we have 0, 0, and 1. Right, so that's our matrix C, and if you look here, that's what it looks like. Right, then we need to create this vector B where we have zeros in the first two positions, and in the last one we have the mass flow rate of stream 3. So for B we can write 0, 0, and let's choose a value of 5 kilograms per second for flow rate m.3. So that's our vector B. So we said that the solution is given by m dot being equal to the inverse of C times B, and we can get that here. So M equals I N V C times B, and that's the answer there, 145. So let's look for that on our set of graphs here. So you see for a value of 5, I'm sorry, this figure's very small, but here we have M3 being 5, and you can see here this is 2 and that's 0, so this must be the value 1, so that's 1 for M dot 1 and 4 for M dot 2. So we've got the solution that we expect if we choose the value of M dot 3 to be 5. So that is giving us the right solution. So if we put it in vector matrix form, we can also easily develop the solution there. Now, of course, as we talked about, the inverse of a matrix is computing the inverse of the matrix is a computationally inefficient way to solve this problem. Generally speaking, it's better to use LU factorization, and I'll leave it to you to look up the LU factorization notes and to apply that to this same problem. Now, something we should realize from this problem is that we didn't see much difference between the amount of effort we had to make in the two approaches. Right, in the first approach, where we did a manual back substitution to solve for those mass flow rates, there wasn't much difference between the effort in that and the effort we had to put into creating the matrices and inverting that matrix and solving. Right, that's because the system is simple enough that it's fine for us to try to solve this one manually. Let's look now at a problem in which the system is larger and it isn't as easy to solve by hand, so to say. Right, so that's what we're looking at in this example. So we're interested now in a larger multi-node system, and in the process that we're looking at, we have here 3 units. Right, this might be a reactor, that might be a separations column, perhaps that's a filter, and we have a fresh stream entering here, and this stream 1 joins with stream 9, which is coming from later in the process, so that's a recycle stream. So this recycle stream joins with stream 1 to give us stream 2, and that enters unit B, and we get out stream 3 here, and then this stream 3 joins with this another recycle stream 10 to give us stream 4, and then stream 4 enters the unit D here, and from unit D we have 2 streams coming out. Right, some separation will happen and we'll get 2 streams, streams 5 and 6 out here. So then stream 6 goes down here, and then that splitter will again separate that stream into stream 7 and a stream 8, which goes off in this direction. So stream 8 will split here into streams 9 and 10, and we want to develop the flow rates for all the streams across the system using again our material and energy balances, and we'll see that this time formulating this as a vector matrix problem makes a significant difference to the amount of effort we have to make in solving this. So let's first develop the system of equations for developing the mass flow rates through all the streams here. So let's look at a balance on the first node here, namely the balance around this mixing point. So we can see we've got stream 1 entering and stream 9 entering and stream 2 going off. So that's m dot 1 plus m dot 9 gives us m dot 2. So that's the first equation that we have here. So that's the balance around node A. And then for node B here, you can see that we've got the same mass flow rate coming into this unit as going out here. And so that's the equation that applies around node B. And of course here we are just looking at the total mass. We aren't counting any change in the number of moles of the species here. So the total mass must be conserved even if there's molecular rearrangement going on. Right? If there's reaction happening that's changing the nature of the species involved, it doesn't matter to our total mass balance. The total mass in must be the total mass out at steady state. So that's the balance across the reactor. And then if we look at node C here, you can see that